I just want to show you a quick demo of k-means clustering in a real world application. Okay, this software is OpenDragon, which is a remote sensing image processing package, a package for analyzing information from satellite images that my partner and I created quite a long time ago, mostly for use in education. And one of the things you can do with satellite images is you can use clustering to segment them based on their radiometric structure. What do I mean by radiometric structure? Satellite images, satellites, Earth orbiting satellites, measure radiation that's reflected from the Earth. And the sensors that they use are set up so that they measure the reflected radiation in a series of narrow wavelength bands. So there's one sensor that measures blue, one sensor that measures green, one sensor that measures red, and there are also sensors that measure bandwidths that are not in the visible spectrum, like near infrared. And using the pattern of values across the different bands, we can identify different things on the ground. So this is a natural color image of Lamtakong Reservoir in Korat. And as you can see, here we have some agriculture, here we have the water. Okay, here we have some built up area. And the colors come from the combinations of the values for reflected radiation for the different bands. So water absorbs almost all radiation in the visible range. So water, clear water, always comes out looking very dark because it doesn't reflect back a lot of radiation. In contrast, built up areas, places that are like concrete, they reflect back almost every band of radiation. So they look white. Okay, areas that are vegetated absorb red and reflect green. Okay, so the pattern for each pixel across the different bands is going to vary depending on what's there on the ground. So we can use this information, use these values on the different bands as features in machine learning, and we can do both supervised and unsupervised machine learning using satellite imagery. So today I'm going to very quickly show you how we can do k-means clustering on this image. So we have to tell it what image we want to use. And even though when we're displaying an image, we can only use 3 bands for red, green, and blue, we can actually put more into the clustering. Okay, I'm going to say that we want 5 clusters, maximum and minimum. Dragon has the ability to drop clusters if they don't have any pixels in them. So that's why we have a range. Okay, I'm going to use 30 iterations, and I'm going to say that I want it to ask me whether I should continue every 10 iterations. So here we go. And by the way, this image we're looking at is 1000 by 1000 pixels, which means it's about 1 million pixels. That's important because if we look at this table, we see that the number of changes from one class to another in the last round was about 28,000. So even though that seems like a large number, what that means is that most of those million pixels are in fact already stably assigned to a cluster. But let's keep going. I don't think I did that right. I don't think I did keep going. Anyway, here's our results. Okay. And this is the result from last time. So you didn't see that. And here, okay, we've color coded the 5 different clusters. Now we don't know what those clusters are, what they mean. But if we compare that image with the original image, redisplay the original image in a different window, we can see that the clustering actually did do a good job of finding the patterns in the images. You know, we have one cluster, which is clearly the water. Plus, you notice that this is not water. This is actually just an area that's in shadow, but this also got put into the same cluster because the values of the features were similar. Okay, we have another cluster that's the very bright areas, mostly the built up areas. Okay, we have another cluster which is the vegetation, that's sort of aqua color, and so on. So let me run this again and run the full 30 iterations, just so we can see if we get a different kind of result. That'll be kind of interesting, because it's pretty fast. Clustering, I want to use the same images as before. So at each point in the image, at each pixel, each of these 4 bands is going to contribute a value. So we have 4 features. Same number of classes. Okay. And it's 30 iterations. And ask several times. And we want to put this in, we want to compare this. So this is viewport 1, right? So we put it in viewport 1. Okay. So it's running. Okay. So after the first 10 iterations, we've got about 28,000 pixels have changed in the last iteration. Let's run it for another 10. Okay, notice we're down to only 8,000. Okay, so the more iterations we run, the more stable this clustering becomes. Okay, and finally, we have our final results. And this result, by the way, tells you how many pixels and what the classes are. And we could find out also what the centroids were if we wanted to do that. So let's just compare the 2 results and see how different they are. Not very different, but I would say the one on the left is better. I would say that it's better because the clusters have more coherence to them. There's less fragmentation. Anyway, this is just one real world example of how we might want to use clustering. And by the way, you can download OpenDragon from opendragon.org. And if you want more information, just ask me. Thanks.